Hello, everyone, and welcome back to Kognito Key. I am so excited to have you here today because we're completely deconstructing a really fascinating piece of engineering instrumentation. It's the photoelectric tachometer. If you've ever stared at a spinning motor shaft and wondered, how on earth do we precisely calculate its speed without adding bulky mechanical gears? Well, you're in exactly the right place. So, I want to start by posing a really simple question to all the brilliant engineering minds watching right now. How do we measure rotational speed with literally nothing but a beam of light? It sounds kind of like magic, doesn't it? I mean, we aren't using physical gears grinding against each other, and we aren't relying on magnetic fields. We're just using light. And honestly, this brilliantly illustrates the elegance of modern engineering. We're taking something weightless and frictionless to measure heavy, high-speed mechanical motion. It's so cool. All right, let's dive into the formal definition real quick. A photoelectric tachometer is, simply put, a device that uses light for measuring the speed of rotation of a machine's shaft or disc. That's the fundamental principle right there. Light is our absolute secret tool here. By analyzing how a spinning object interacts with a continuous beam of light, we can accurately capture its rotational speed. And we do it completely contactless. To really wrap our heads around how this works, we need to break down the physical anatomy a bit. There are basically three absolutely essential components to this hardware. First, you've got an opaque disc with a series of equivalent holes placed evenly all around its outer edge. Second, there's a light source, which is often a laser or an LED. And third, a light sensor placed perfectly opposite to that source. Just three simple parts working together to create something incredibly precise. Now, what makes this whole setup so brilliant is the geometry. The alignment is absolutely critical. The opaque disc is physically mounted directly onto the rotating shaft. That's the very shaft whose speed we're trying to measure. With the light source on one side and the sensor on the exact opposite side, the solid parts of the disc act as a physical barrier. So light has literally only one path it can take, straight through the holes when they perfectly align. Let's picture this in action. Imagine the motor turns on and the disc begins to rotate. Because of those alternating holes and solid opaque sections, the light sensor experiences this dynamic strobe effect. When an opaque portion passes by, the light is completely blocked, right? And the sensor output drops to 0. But then, a split second later, a hole aligns perfectly with the light source. The light passes right through that hole, hits the sensor, and boom, suddenly an electrical pulse is generated. This constant alternating sequence of light and dark creates a continuous stream of distinct electrical pulses. Okay, so what actually dictates the frequency of these pulses? Well, the production of these electrical pulses depends on only two factors. First, the number of holes on the disc, and second, the speed of its rotation. Since the number of holes is a fixed physical characteristic, it doesn't change, the only variable left is the speed. Because of this, the rate at which these pulses are generated is a perfect, direct mathematical reflection of exactly how fast that disc is spinning. Of course, having a steady stream of electrical pulses is great, but we still need to translate that into a readable number for the engineer or operator using the device. And that is where our final piece of the puzzle comes in, the electronic counter. Think of this counter as a tiny internal computer that takes over at the very end. It just sits there, rapidly tallying up all those electrical pulses coming from the light sensor and translates that exact pulse rate into RPM, or revolutions per minute. Let's move on and talk about why engineers actually choose this tool over others. There are massive advantages to this system. First off, the output is inherently digital. It's either an on pulse or an off zero. Because we get this direct digital output voltage, we completely eliminate the need for any complex, expensive analog to digital converters in our circuits. Plus, because it's literally just light turning on and off, the pulses have a constant amplitude. This makes the downstream electronic circuitry incredibly simple, super clean, and really reliable. But as we all know, no engineering solution is 100% perfect. We definitely need to talk about the physical limitations. 50,000. Now that number represents the approximate lifespan in hours of the light source used inside the tachometer. While 50,000 hours is a really long time, it's still a definitive physical drawback. Eventually, that bulb or laser will inevitably burn out and the light source will need to be replaced. So yes, there is for sure an ongoing maintenance requirement for this device. Furthermore, we have to consider the accuracy of the whole system. The accuracy of this photoelectric method depends heavily on something called the unit pulse error. Basically, if the counter misses a pulse or maybe counts a fraction of a pulse as the hole passes by, the speed reading will be slightly off. But engineers are super clever. They minimize this error by using a specific gating period.
This means the meter carefully measures the frequency by counting those input pulses over a very specific, controlled window of time. Alternatively, counting the total number of pulses generated over one complete, full revolution is also used to minimize these errors and ensure top-notch accuracy. So let's weigh it all up here. On the pro side, you have this brilliant non-contact measurement tool that provides a super clean digital output with incredibly simple electronic circuitry. It's fast, it's efficient, and it doesn't cause any mechanical drag on the motor it's measuring. On the con side, though, you do have to deal with the inevitable burnout of your light source after about 50,000 hours, and you definitely must design your electronics carefully to account for those unit pulse errors using gating periods. Ultimately, using a simple beam of light to track high-speed mechanical rotation is just a truly beautiful piece of clever engineering. It takes something really complex and solves it with total elegance. Well, I really hope this explainer helped you visualize exactly how a photoelectric tachometer works from the inside out. Thank you so much for joining me today. Keep learning with Kognito Key. If you found this explainer helpful, please hit that subscribe button, like the explainer, and share it with your fellow engineers. But before you go, I want to leave you with this thought. As our machines push toward even more extreme, hypersonic speeds in the future, will traditional light sensors be able to keep up with those crazy pulse rates? Or will we need an entirely new spectrum of measurement? Think about that. See you in the next one.